All right, so let's go through some calculations right here. This is basically the force diagram. I've got two forces acting up here and here from the force scales, and I've got these two forces acting down. This is the mass from the weight of the meter stick, and this is the weight of the mass I hooked onto it. And so now, what I want to do is take a look at the sum of the forces and sum of the torques. Sum of the forces is easy. It's an equilibrium. The sum of the forces is equal to mass times acceleration, Newton's second law. That hasn't changed, except it should be equal to 0 because there's no acceleration. Now, the sum of the forces, well, up, I have 1.96 minus 1.96 minus 1.05 plus 0.735 newtons. Well, they're all newtons. That should be equal to 0. It's actually not going to be 0, but we'll just see how close we get. So, and we end up with negative 0.315 is equal to 0. This is the new math, because physics is right, so math must be wrong. No, this is just, there's some experimental error there. The total force that's acting up, 1.96 and 0.735. The total force acting up is 2.695 newtons. That's what's acting up. The force that's acting down is 3.01 newtons. Those should be equal. So I could find I don't know which one is more accurate. I'm actually believing that in this case, that the force down is more accurate because the force up depends upon these force scales right here. But let's assume that we don't believe that. And we can find the percent difference. How far off are we? So it's just the difference divided by the average. And we end up that the difference, they should be equal, but we are off by 11%, which is not too bad for a physics experiment here. So that's the sum of the forces, but now let's deal with the torques, because that's the new part. And so I'm going to erase this information right here. Assume that you can always just still frame it and zoom in if you have to. The sum of the torque should also be 0. The sum of the torques is equal to I alpha, which should be equal to 0. Now I want to find the torques, so I need to find a pivot point, and I'm just going to choose this right here, this point right here at the 10 centimeter mark to be 0. I could pick any point that I want, but I'm going to pick this one right here, and I'm going to highlight it in green. At least it should look green to me. That's my axis of rotation right there. And so now if I want to find the forces, I want to find the torques, I mean, so I just do each one at a time. And this is why having the beam parallel to the ground was important, because it makes finding the torques a lot easier. All I have to do is multiply the force times the moment arm, keeping track of pluses and minuses. I don't have to worry about the sign of any angle or what component is actually acting there. Now for this, I'm going to use the convention that up is positive and to the right is positive. And so the torque from this first one, 1.96, that's positive 1.96 times 0, because the distance to the axis is 0, plus, next one, negative 1.96 times 0.2 meters, that's 30 centimeters minus 10 centimeters. And I'm going to need some running room here. Plus, I'm just adding up the next torque right here, it's negative 1.05 times 48.7 minus 10, or 0.387 meters. Plus, and then the last one, the force, it's up, so it's positive, so positive 0.735. And then the distance is 80 centimeters, or 0.80 meters. And we'll see how this one goes. Let's see, so I know that this one is 0, 1.96 minus 0.392. That's Newton meters because I'm doing everything in SI here, so that's 1.96 newtons, 0.2 meters, so that's Newton meters, minus 1.05, 0.387, minus 0.406, we'll just take that for 0.406 Newton meters, and then lastly 0.735, enter, 0.8 times 0.588 Newton meters. Obviously, it's not going to come outright. We're going to be further off on torque because there's a lot more things involved here. But this is the essence of the analysis, but you guys will get it right tomorrow. So the total torque that's acting clockwise here, about this point, both of these forces right here are trying to rotate it clockwise. So the direction of the torque into the board, we represent that here with a minus sign. So that's 0.392, 0.406, 0.392. So negative 0.798 plus 0.588. This is the sum. This is the clockwise torque. This is the counterclockwise torque. This last one is from this force right here, trying to rotate it counterclockwise. That should be equal to 0. It's not, obviously. So my percent difference between these magnitudes here, because they should be equal in magnitude, just opposite in direction here, that's not a Newton's third law thing, is let's see, 0.798, enter, 0.588. And we end up with the difference between it, the percent difference is a 30% difference. I'm not too shocked by that, but that's the essence of the analysis right there. Looking at the sum of the torques, and again, the torques that are trying to make this thing rotate clockwise, counterclockwise should be equal to the sum of the torques trying to make it act clockwise. And that's tomorrow's lab.